Okay, welcome back to this section of HUP 112, Logic and Philosophy. My name is Dr. Richard Brown, and today we'll be continuing our discussion of natural deduction and extending our ability to to offer new and interesting proofs. So you may recall from last time that we extended the rules that we were using, the rules of implication. And what those allow us to do is to write something new based on what's already there. So we have modus ponens, modus tollens, hypothetical syllogism, disjunctive syllogism, and then our four newish rules that we talked about last time: simplification, conjunction, constructive dilemma, and addition. So today we're going to introduce four new things, but these things are not going to be rules of implication, but they will be something called axioms of replacement. And the axioms of replacement allow us to manipulate or change one string of symbols into another string of symbols. So, for instance, we'll talk about De Morgan's rule, which tells us how to handle negated dotted set statements. And we'll use this convention that the book uses of using the double colon to mean logically equivalent to. Now, a lot of times you would find them using the triple bar, or you might find some other notation, but the book that we use uses this double colon, and it's fine. So what happens with De Morgan's rule is that you take the tilde, you move it inside, and you change the sign. You change the operator, you change the operator from a dot to a wedge. So instead of tilde p dot q, you get tilde p wedge tilde q. And of course, we have the same rule for the wedge operator, which tells us that if you have tilde p wedge q, that you get tilde p dot tilde q. That's De Morgan's rule. It's a very useful rule. And you might have think that this is a bit surprising, but of course we can easily prove that this rule is true using our truth tables. And so let's go ahead and do that. So if we have our statement P and we have our statement Q, we have our four conditions here that we can write down, and then making sure we capture every permutation. Okay, so now let's take our first statement here, which is tilde p dot q. Okay, and our second statement here, which is tilde p wedge tilde q. And then we're just going to compute the truth values for these statements and compare them to make sure that these in fact say the same thing, so to speak. So let's start with this one here. We'll write down compute the truth value for p dot q, and then compute the truth value for tilde p dot q. So p dot q has the truth table for a conjunction, so we know it's true when both of them are true and false in every other case. And then of course the negation sign reverses that, so what was true turns out to be false, and then true in every other case. And so that's the truth value that could possibly result from tilde not both p and q, which is how you would say that in English. But of course, another way of saying not both p or q is this way over here. So let's compute our truth values. First of all, by computing the tilde signs here and then using those to get the main operator. So here we reverse the p, so we have false, false, true, true. And here we reverse the q, so we have false, true, false, true. And now we'll use these two columns to use the rule for disjunction. So false, false, that's false, false, true, that's true, true, false, that's true, and true, true, that's true. So now notice, false, false, true, 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 true. And so what we've just proven using our truth tables here is that these two statements have the same meaning. This statement literally says the same thing as this statement, at least truth functionally. There's no distinction between them. So wherever you find one, you can write the other. And that's what De Morgan's rule says, named for the person who discovered this. Augustus de Morgan. So wherever you see not both P and Q, you can write not P or not Q, and vice versa. So the important thing to remember about the rules of replacement, and one of the ways in which they're very different from the rules of implication, is that the rules of implication work one way. So if you have P horseshoe Q and you have P, then you get Q. That's modus ponens. But you can't go the other way. This works this way. You can't go from Q and get P and P horseshoe Q. Whereas you could start from here and write this, or you could start from here and write that. These things are interchangeable, and the axioms of replacement tell us which ways we can interchange things that preserves the original meaning. And if you ever are in doubt about which of these things work, you can always just write out the truth table and compute the truth values and check to make sure that they are in fact the same. Boom. So that's De Morgan's rule. It works both ways. Commutativity tells us that you can reverse the order of disjunction and conjunction. So if you have P wedge Q, that is logically equivalent to Q wedge P. And you might think that that's annoying, but you need that rule if you want to use disjunctive syllogism. You have tilde Q and you want to get P. You'd have to use commutativity and reverse the role of them. And of course, the same is true for conjunction as well, Q dot P. So those are logically equivalent. Now, associativity is a way of moving parentheses in statements which have two of the same operators, namely two of disjunction or conjunction. So suppose you have P wedge Q wedge R, P wedge Q wedge R, and suppose that that was originally written like this. Well, associativity says that you can move these parentheses over and preserve the truth value, so that's equivalent to P wedge Q in parentheses wedge R, so that the parentheses have just been moved over here, and you can verify that with truth tables. I'm not going to go through it, but of course the same is true here with a P dot Q dot R. That's logically equivalent to P dot Q dot R. Now, the important thing to remember about associativity is that the operators are the same. So you have two wedge operators, two dot operators. The distribution rule is a different rule involving when you have mixes of these things. So suppose you have P dot Q wedge R, and you want to distribute this P amongst these terms, then you get P dot Q, and you keep the dot goes inside, so to speak, and the wedge comes out, and then you get P dot Q and P dot R. And the same here is true if you have P wedge Q dot R. That's logically equivalent to do the same thing here. You have P wedge Q, and that's going to be dotted. So you change the main operator, that's going to be dotted to P wedge R. That's the distribution rule. The important thing to remember is it goes this way as well. So if you have, and one thing I see students struggle with a lot of times is that they'll start with a sentence like this, P dot Q wedged to P dot R, and they won't see that they can pull the P out, so to speak, and get P dot Q wedge R, which is important if you want to get P on a line by itself. This is a way to do that. And again, if you want to verify this with the truth tables, then you can. So we have one final rule that we need to add to this, and that's our double negation rule, which tells us that P is logically equivalent to tilde tilde P. So tilde P says that P is false, tilde tilde P says that it's false that P, or in other words, just the case, P is the case. So now we have our 8 rules of implication, and we're adding to that these 5 rule axioms of replacement, which allow us to change things around. Now, one of the things that sometimes people forget about when they first come to this is suppose that you have a statement like this. Suppose you have S horseshoe tilde T dot U. Suppose you have that on a line let's call it n. Well, suppose you just wanted to change this for whatever reason. You could have the next line say S horseshoe and then change that to tilde T wedge tilde U. And you could say that you got that from line n by De Morgan's rule. So you can work inside of statements using the axioms of replacement, but you can't do that with the rules of implication. So if you have A horseshoe, B horseshoe, C on some line n, and then it would be wrong to write on the next line, and suppose on the next line you had B, and then so you wanted to write on the next line C, and say you got that from modus ponens. You cannot do that without first getting this on a line all by itself. So you can't go in and say, this makes modus ponens. And that's something to keep in mind when you're using these rules. Okay, so let's go through some examples here. So here is an example from the book. Now remember, I'm going to write our rules over here. So we have modus ponens, we have modus tollens, we have a disjunctive syllogism and hypothetical syllogism, we have constructive dilemma, we have simplification, we have addition, and we have conjunction. And now we're adding to that, De Morgan's rule, associativity, commutativity, double negation, and distribution. So that's not the order I gave them in before, but this is just to remind us of what the rules are. And so any one of these could be used in a proof. So let's go through some examples. Suppose we have our first sentence here. Our first premise says A horseshoe tilde B dot C, and that's in parentheses. And our second premise here is A dot C, and our conclusion is tilde B. Okay, so we always start in the same way by looking for the conclusion somewhere in the premises, and we see B here, but it's in here, so we can change that using our De Morgan's rule, just so that we see what's going on. We can write A horseshoe tilde B wedge tilde C, and we got that from line 1 by using De Morgan's rule. So now we can see tilde B here, and that's good because we're going to want that for something, and we want to get that tilde B out of here, and so probably what we're going to need to do is get it from here. So let's anticipate that and change this around. So line 4, we'll write A horseshoe tilde C wedge tilde B, and we did that by commutativity. So we just, line 3, by commutativity. We simply switch the order in anticipation of what we're going to do. So now we see that if we had A around, we could do modus ponens, and we can get A here using simplification. So we write line 5, and we write A, and then we got A by simplification on line 2. Okay, so now we can do modus ponens here. Now notice, we could use modus ponens on lines 3 or 4. We could use it on either one. They're both there, and they are both true according to what we're doing here. But if we use it on line 3, we'll get this, and then we'll have to reverse it. So we can plan ahead. So we've already reversed it, so we may as well use it on line 4 and write down the thing that we really want, which is tilde C wedge tilde B. And we got that because lines 4 and line 5 are modus ponens. So now we see the conclusion is here. That's what we wanted, tilde B. We have that. So we have to use disjunctive syllogism. But remember that our disjunctive syllogism rule here says that if you have P wedge Q and you have tilde P, then you can get Q. So here we have P, this is our P term, wedge Q. So in order to do this, we somehow need to get a C. Okay, but we've got to have a tilde in front of this, so it would have to be tilde tilde C. So we see C here. We know we can use double negation to turn that into tilde tilde C. Now, can we use simplification to get it out of here? And the answer, of course, is no. We have to use commutativity to reverse the order. So we can write C dot A, and we can say we got that from line 2 by commutativity. So now we're on our way. We can write line A. We get that C. We got that from 7 by simplification. And finally, we can write line 9 here, which is tilde C. We got that from line 8 by double negation. Now we can use line 9 and line 6 and get the thing we really want. So line 10 here, we write tilde B, and we got that because 6 and 9 are disjunctive syllogism. And now we've shown that the argument follows. Okay, so let's do another example using our rules here, and then we'll start looking at some translation exercises before we finish. So here's our first premise. It says D dot E wedge F, and these are in parentheses. And our second premise is tilde D wedge tilde F. Second premise, tilde D wedge tilde F. And our conclusion is D dot E. Okay, so as always, we want to start by looking at what we can do here. And so we see our tilde D wedge tilde R. That's interesting. Excuse me. Tilde D wedge tilde F. So that's interesting. And it looks like we can do something with that. So we can use De Morgan's rule on that. So let's just do that simply because we can. So we can get tilde D dot F. That's interesting because it might do us some good. So we can see a way of getting D dot F up here. So we can take line 4 here and change this. So that would be D dot F wedge E. And we did that using commutativity, simply switching those around. So line 1 by commutativity. Oh, and this was, by the way, from line 2 by De Morgan's rule. Okay, so now we can move this in here and use the distribution rule here. So that would give us D dot F wedge D dot E, D dot E. There we go. And we have tilde D dot F right there, and we have D dot F. So we can use now our disjunctive syllogism and get the conclusion that we want. So we can write D dot E, and we got that because lines 3 and 5 are disjunctive syllogism. And this one, I guess we should write that we got from line 4 by distribution. Another example here. First premise here, which says G dot H wedge G dot J. G dot H wedge G dot J. That's our first premise. Our second premise here is G wedge K horseshoe L. G wedge K in parentheses horseshoe L. Our conclusion is L. Conclusion L. All right, so we see what we have to do here. Somehow we've got to get G wedge K on a line by itself, and then we can use modus ponens and get L. So how do we get G wedge K? Well, we have G and we have no K. So how are we going to do this? Well, it looks like we can get G, and then we can use addition to get K. So let's see how that works. Let's write line 3 here. Now remember, addition, the distribution rule allows us to take out this G and dot it to the wedge of these two. So we can write G dot H, that's an H, H, G dot H wedge J. And we did that using the distribution rule, but going in the opposite direction. So our distribution rule here says if you have P dot Q wedge R, that's logically equivalent to P dot Q wedged to P dot R. P dot R. And typically, people think in moving in this direction, starting from here and transforming and getting this, computing that according to the replacement. But of course, here we went the other direction. We started over here, and we ended up with this statement here, which is perfectly legitimate. So you don't want to think of these in terms of going in one direction, but going both ways. You can use them to interchange these back and forth as many times as you want. All right, so now we have G dot H wedge J, and now we can write line 4, which is our G here, and we got that from lines 3 by simplification. Now, we want to get L here, so we don't have a K, but of course we can use addition, and G wedge K from line 4 by addition. Very handy. And now we have G wedge K, and we can derive L on line 6 because lines 2 and 5 are modus ponens. Let's look at another one of these here. It's good to do as many of these as you can. Of course, you won't really get the hang of this until you start doing these yourself. But it's good to get some idea of what you should be doing. So let's suppose we have M wedge N wedge O here. That's our first premise. Our second premise here says tilde O. Okay. And our conclusion is M wedge N. Our conclusion is M wedge N. Okay. So we look up here and we see, aha, well, this one is fairly straightforward. We can use associativity, group M wedge N together. That'll be wedge to the O. We have tilde O, we'll flip them, we'll use disjunctive syllogism, and we'll get our M wedge N just like we want it. So let's go ahead and do that. So we write line 3 here, we use associativity, and we move the parentheses over M wedge N, wedge O. And we got that from line 1 by associativity. Okay, now, of course, we have to flip this, O around the new main operator, M wedge N, and we got that from line 3 by commutativity. Okay, now we have tilde O and we have O. We can use disjunctive syllogism and get M wedge N, M wedge N, and we got that from 2 and 4. 2 and 4 by disjunctive syllogism. So that one was fairly straightforward. Let's do one that's a little bit less straightforward. Okay, let's do one that's a little bit less straightforward. So suppose that your first premise was K, horseshoe, F wedge B, F wedge B. And our second premise is G dot K, and the conclusion here is F dot G, wedge B dot G. F dot G, wedge B dot G. B dot G. And that's in parentheses. Okay, so we look at this, and the first thing that we notice is, well, the conclusion doesn't seem to be contained anywhere in the premises. So we need to know what to do. But of course, we see that the thing that we have as the conclusion, F dot G, wedge B dot G, well, it seems like we could work backwards from that and try to figure out how it might be arrived at from the from the premises that we have up here. So the first thing that we notice is that we see G and we see G. So we can reverse the order, and I'm just going to cheat a little bit and write this as that. Do 2 of them in one step, which technically we won't be allowed to in the Applia program, but we can do that here. And then, of course, that's a dot. Then, of course, we can just use distribution and get the G. So that would be G dot F wedge B. Well, there we go. Now we see F wedge B. So we see that, and we see G right here. So it looks like if we got G and if we got F wedge B, we could put them together and then use the reverse of this to get the conclusion. So then that gives us a strategy for constructing the proof. And that's a useful kind of tip to keep in mind. There are cases where you want to start with the conclusion, and if you can't find it in the premises anywhere, you use the rules of replacement to work your way backwards and see what you should do there. So that seems relatively straightforward for us now. So we write line 3 here, and what we want to do is get K, and then that will give us this. But we're also going to want to get G. So we may as well use our simplification and simply get G on this line because we're going to use it later. So we can write line 4 then, and we want to reverse these. And we did line 2 using commutativity, and we did that so we can also get K on a line by itself. Now we use K on line 4, simplification on line 4 to get K. And that's good because now we can get F wedge B. So now we write 6, we use K in line 1, and we get F wedge B. And we got that because lines 1 and 5 are modus ponens. Modus ponens. And now, of course, we're done, almost. Now we can take F wedge B and we can take G, and we want to put them together. So we write line 7, and we have G dot F wedge B, and we got that from lines 3 and 6 using conjunction. 3 and 6 using conjunction. Using conjunction with the J. Okay, so now we've set ourselves up to go ahead and use distribution. So now we can move this in here, line 8, and we use distribution G dot F, and that's going to be wedge to G dot B, and we got that from line 7 by distribution. Okay, so now we're almost done. We have the conclusion basically, but we just need to put it in the right order to make sure that we've got everything done correctly. If we just stopped here, we wouldn't be finished. So now we write line 9, and let's reverse this one first. So we write F dot G wedge G dot B, and we got that from line 8. Commutativity, and you would like to do this one as well, but while some people will allow that, the system that we're using doesn't allow that. So you have to use a second final step here, writing line 10, F dot G wedge B dot G, and you got that from line 9 by commutativity, and now we have derived the conclusion from those premises. So that was a little bit more difficult in that it required us to analyze the conclusion. So those are a bit of strategy tips that you want to start with. You always look at the conclusion, and you look to see whether you can find it. You look at what the conclusion is, what kind of statement it is, and that'll give you a clue to how you're supposed to prove it. And if you can't find it, then you want to just start toying with the rules, manipulating various things to make sure, to see, if there is a possible path. We'll usually